Alrighty, and we are back. Let me. Oh, we want the other side. There we go. All right. Contrary to the words I said in the last lecture, this one is actually this section we're going to look at is linear first order differential equations. So linear first order differential. And I'm actually just going to go straight into examples. We'll look at this because you'll see there's kind of, well, there's a nice continuation from the last section. So let me find this. All right, so let's try start something. So this is three other exercises, dy dx. Oh, actually, is there? Oh, sure. Plus y. All right. Plus y. Good. Let's see. Mm. 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 Let's um, okay. All right. So we're going to see quite a few more of these, but I want to give, again, like I was saying on the last lecture, I want to give you guys an idea of, yeah, just why they call this linear. Um, so, so essentially the idea is, your coefficients in front of both your derivatives of y itself. One, they can't be a function of y. Can't be a function of y. They can't be basically a nonlinear function of x. And then the third restriction is basically you can't have y or really any of these derivatives raised to a nonlinear power. So basically anything above the first power. Again, like I was saying on the last video, it's kind of interesting. Linear and differential equations really has nothing to do with, or just is not very similar to what you see for algebra. And in fact, yeah, even in something like class of linear algebra, their definition of linear there is not really the definition of linear here. Um, so, so I mean, we can see it's a first order differential equation. The coefficient in front of y here is a nice constant. So this is definitely qualifies as linear. Again, other things could qualify as linear, but this definitely qualifies as linear. Um, So nice little constant coefficient. So basically constant coefficients definitely linear. In this case, first order differential equation. All right. So notice also that this kind of looks a lot like the problems from last time. However, so what I'd like you guys to do is see if you could try to solve this. So let's say it kind of looks like a separable equation. Let's see if we could solve it that way. So let's see if we could isolate the y with the dy and the x with the dx. So I want to give you guys a second to do that. So go ahead and pause on your side. I'll pause on my side. See if you can solve it using separable equation. So I want you guys to try. Could you solve it that way? Could you separate y's with the dy's and the x? Yeah, so hopefully you found that you could. And because that's actually the thing we need to see here. So I guess what I'm saying is this does look decently like our equations that were separable. Looking back, if you look back at the exercises, there definitely was less additions and subtractions kind of present in those equations, but there were still, there were some of them that had addition and subtraction and worked out fine. The algebra that where how things were, how things were set up and organized, you were able to add and subtract things to both sides and then multiply and divide off pieces. But it ends up with this one, there's just no way to do it because let's say we move the y to this side, then if I try to get the dx multiplied over here, it's going to have to multiply with the y. And that y then becomes kind of stuck with this x because it's being subtracted from all of this. So no matter how you kind of rearrange this algebraically, you can't get the y with the dy by itself and the x with the dx. So that's fine. So part of the reason I do that too is, let's say you get to a test on this. Part of what I'm saying is you're not going to be able to look at this and be like, oh, it's definitely that type of differential equation, and therefore, this is the way I'm going to go solve it. You're not always going to see that to begin with. So you're going to try, and if it doesn't work, that's fine. Pull back, regroup, figure out what the other method is that you need for the problem. So you look at this, maybe it looks like separable, and it isn't, and that's fine. So what we want to look at today, though, a linear first order differential equation, like I said. So first order differential equation with, in this case, constant, you can have things other than constant coefficients, but especially if you have constant coefficients in front of your derivative and your y or whatever is present there. This way of writing out a linear first order differential equation is kind of what they call the standard way of writing it out. When I say standard, so what they mean by that is they want to see a derivative here, they want to see a y here, they want to see the derivative with nothing in front of it, basically. So that's kind of the key, is derivative with nothing in front of it and a y here, and whatever you want over here. So if it's written this way in the standard form, then so there's as long as it's in standard form, there's actually a general, the nice thing about this is there's a general approach that as long as it's linear in first order, you got it in standard form. There's a general approach that will solve all of these, all differential equations that fit that kind of form. So the way we go about solving this, so the first thing is you want to identify what's in front of y, because that is this, they use a p to represent the function, but that's this kind of p of x function. And so what we're going to do with that, once we've identified that, you're gonna figure out what e to the integral of px dx is. Let me make sure I got that part correct. Sometimes I don't remember format correctly. Yeah, I got it. And this little piece here, so we call this the integrating factor. You'll see we'll actually use this integrating factor in a couple other sections, a couple other types of um, differential equations actually use integrating factors as part of their process to get to the answer. Again, because it's a 5-week course, I don't want to go back kind of behind the theory on this, or even the general theory and use of integrating factors. In some ways, also all I'll say about it is some ways is what we're doing is they're a clever parts or a clever piece that we're going to multiply both sides of this equation by. So if you figure out what this is, I'm going to multiply both sides of this equation by that. When I say clever piece, what I mean is they sort of transform the equation into one that is easier to take a derivative of. So essentially, they transform this into a separable equation. Like I said, we started out thinking, I was asking you, is this separable? It looks kind of like it is. We figured out, no, it's not separable. So essentially, what we're doing is we're picking a clever piece. We're making this kind of clever piece that if we multiply both sides of the equation by it, then suddenly that equation is separable. And again, when that works for solving, because we're multiplying both sides of the equation by the same thing. So we're not changing anything there about the equation. We're going to get the same solution. So it's really kind of a cool idea. And so again, the math behind it is essentially there's algebraic and calculus manipulations of this equation that essentially the general form of this equation that every time kind of gives you this integrating factor. So they figured out, well, if we could multiply both sides of the equation by the integrating factor, then we can essentially give it exactly what it needs to become a separable equation. So we started with a section on separable equations. It kind of looks like a separable equation, but it isn't. But the joke for today, the punchline for today is if we can figure out this integrating factor, then when I multiply both sides of the equation by that integrating factor, I get a separable equation. And we're good. We're great. But we can solve that. So let's figure out what this integrating factor is. So we said P of X is whatever's in front of Y. What's in front of Y? Good. Just a plain one. So my integrating factor is going to be e to the integral of 1 dx, or this dx, if you want to put it that way. But either way, when you integrate dx, what do you get? That's an x. So my integrating factor is e to dx. So what I'm going to do then is I'm going to multiply both sides of the equation by e to dx. Multiply e to dx times all this. Equals then e to dx times e to the 3x. So we end up with, that don't even probably need to multiply through, but dy dx e to dx plus e to dxy equals e to the 4x. And then, that was a little bit like I was talking about in the last lecture. Give me a second. And what's the trick here? Okay. Mhm. So, so back to this, it's kind of being very, well, not really weird, but maybe coded by saying this is a very clever choice, right? So why is this a clever choice? So now let's look at the left side of this equation. And I want you to notice something sort of just structurally about the left side of this equation. So the left side of this equation is a function, so kind of it's times the derivative of y, and then it's y times, in this case, some other function. Do you notice something about sort of this structure, thinking back to Cal 2, Cal 1, do you notice something about that pattern that looks maybe familiar, looks like a pattern you've seen before? And maybe you do, maybe you don't. Hopefully what you kind of see here is it looks like I have a function times a derivative plus a function maybe times a derivative. And, but the function each time, so the first time the function is e to the x and the derivatives of the y, and the second time the function is y and the derivative is the e to the x. So remember in this case, the derivative of e to the x is e to the x. So when I'm seeing that e to the x second, I'm actually seeing the derivative. So what I'm saying is the setup of this looks like function one times derivative, so yeah, function one times the derivative of function two plus function two times the derivative of function one. And that setup sounds like the product rule for derivatives. So this setup looks like you're taking the derivative of these two functions being multiplied, because remember on the product rule, when you take the derivative of two functions multiplied, you do first function times derivative second plus second times derivative first, and that's like what we got here. So if I took e to the x and y as my original functions, then I have function times the other's derivative plus other function times the first one's derivative. So that's what we do here is this is a kind of an interesting move, which don't often do, or you haven't often done probably in a lot of other equations you've solved. So what I'm going to do here is I'm not going to do any algebra. I'm going to rewrite this though. I'm going to rewrite this as that product, that derivative of products that we just realized that this is. So this is actually the derivative dx of e to the x minus y. So we're literally treating now e to the x times y as sort of our original, or yeah, sorry, the function we're making the derivative. And how might that be helpful? So what do you see? What could we possibly do from there? Sort of verify there isn't any other kinks that I'm not thinking of. Yeah. And a bit like we talked about at the beginning, so at the beginning of that last lecture, when we we're talking about separable equations, we kind of saw those equations to begin with where we didn't even need to separate stuff because one side was already a derivative, right, basically. So we just integrated to get back up to the original function. So the left side for just dy dx. So in some ways, that's what we have here. We have d function dx. So this is already the derivative of that function, which means all I gotta do is integrate, and that gets me back up to this function. So we're gonna integrate both sides. Again, like I said, the nice thing about this is especially chosen so that, and this is the kicker here, this is really the main thing, is this is the derivative of the product of two functions. But once I have that, I can just integrate it, and I know the answer is that function anyways. So it takes us back to those beginning separable equations we dealt with. So you integrate this, that means that I get e to the ezxy. On this side, again, I no longer we know technically we get a constant, but we know from now on that we don't need to write constants on both sides. You're gonna end up subtracting one from the other, and you just get an overall constant. So we will integrate now this side, e to the fourth. So here's where we gotta do a little work. What would the integral, and this time you don't even have to pause, I'll just pace back and forth for a second. What is the integral of e to the 4x? Good. So the integral of that is going to be what? E to the 4x over 4 plus c. And then notice, can we get y by itself here? Very easily. So we'll divide by e dx on both sides. And we do get, in this case, y equals e to the 3x divided by 4 plus c. I'll do this again. Actually, I'm sorry. Knew there was, like I said, I knew there was some little kink in this. So we're not only dividing this first part by e dx, but we're dividing the second part. And we saw a problem earlier where we had like e to the c or something like that, and we knew those are both constants, so we just called it a constant. Actually didn't matter the structure, there was e being raised to a number raised to a number. They're both set numbers with a number, so we call it c. But here, when you take c divided by e to the x, the x changes. For that one, I can't call a constant. But what I can do is I can basically write c e to the negative x. That's what we have there. We're dividing by e to the x, so we get e to the negative x. That would be the answer. I was just checking. I really quickly sure it works. Good. So that would be your answer there. So as long as your equation is linear, first order, and you've got it in that kind of nice, again, standard format. So first derivative up front without anything in front of it, and then a y equals blah, blah, blah. Then we can run every linear first order differential equation like this. Figure out the integrating factor first, multiply both sides by it. Your left side is always going to come out this nice little trick where the left side is essentially derivative of two functions multiplied together, product of functions. And then from there, it's easy to integrate and solve. All right, so let's try this on a couple more. squares. Which ones we're gonna do? Let's look at something like 5. That's 5. Let's make sure I write this correct. All right, where are we? Y prime strings. Here, what they have written is y prime plus 3x squared y. Keep forgetting everything that it says. So there. All right, equal x squared. So notes. So again, we want to at least try to figure out the type this is. Notice this is a first order, and my God, yeah, I'm trying to like. So it's a first order differential equation. The key then will be, so the constants in front of our y prime or y. There are coefficients. The constant is good. This 3x squared, so this is definitely not a coefficient, right? So we have a whole power term in front of y. However, it's a power term in terms of x. So as long as, even if you don't have a constant there, a coefficient there, if your coefficient is some function, as long as it's in terms of x, we are still a linear first order differential equation. And if your linear first order differential equation has nothing in front of y prime and whatever we want in front of y, but just something in front of y, then it is in standard form and you can go ahead and on your integrating factor, figure out your integrating factor, multiply both sides by that integrating factor, and then work it from there. So this is a linear first order differential equation in standard form. Same setup as 3. It's going to have obviously different functions, so a little different results as far as your integration, but same go. So I'm going to go ahead and have you guys pause on your side. I'll pause on my side. Go ahead and start by doing the integrating factor, and then get as far as you can through this. All right, let's see again. So in this case, again, setting up this little integrating factor, where are we doing here? But so my p of x here is the 3x squared. So that'll be sort of the difference this time. It's not just some nice constant, it's actually a whole power function. So my integrating factor, e to the integral now of 3x squared dx. And you needed to go ahead and integrate that. So what did you get when you integrated 3x squared dx? So hopefully that's easy enough. You'll get x cubed out of that, e to the x cubed. And then we are going to multiply then both sides of this by e to the x cubed. So we'll end up with e to the x cubed y prime plus now plus now 3x squared e to the x cubed y. And now on this side, we're multiplying again by e to the x cubed. So we have x squared e to the x cubed. And then again, the key with this little technique is, again, this is being chosen ultra specifically so that this ends up being the derivative of product of functions. Now I think sometimes it's going to be just wonky to see that, or kind of not easy to see that. But notice this is so if I look at the first term here, I have definitely a function and a derivative. So I'm taking y is my second function, e to the x cubed is my first function. And so if I was taking the derivative of e to the x cubed times y, the first part would be e to the x cubed times y prime. And then the second part would then be the derivative of e to the x cubed. Now we want to think about the derivative of e to the x cubed. That's going to require a little bit of chain rule there. But the derivative of e to the x cubed is e to the x cubed multiplied by the derivative of x cubed. And what's the derivative of x cubed? Good, that's 3x squared. So that's where we're getting this piece here. 3x squared times e to the x cubed is the derivative of e to the x cubed. So that's the derivative of that times y, which means this whole thing is just the derivative. Where's the eraser? Which means this whole thing is the derivative of e to the x cubed times y. Which then means I can integrate it and trust that I just get where I came from, right? So if this is the derivative, if this is the derivative of e x cubed y, then when I integrate it, I get e to the x cubed y. So we will integrate both sides. So on this side, we get e to the x cubed y. Now on this side, notice that, so again, at first this probably looks kind of crazy and wonky, or just like it's not going to work. But notice that, oh, and I'm sorry, there's a dx somewhere in here. Where did the dx go? Oh, well, that was part of this term that I never wrote in. Sorry. So that should be dx. Or e dx. Well, because I really don't need that. Give me a second. That's, we get the idea. There should be a dx here, so you can sort of do all that, do the integral. But integrating this, notice that, so this is going to end up being kind of the inverse of the chain rule, or I think we call it substitution when you're doing integration. That if e to the x cubed is my main function, then the derivative of basically, or if x cubed is what I'm substituting into the e function. Anyways, the derivative of x cubed is 3x squared. So you would need to integrate this. E to the x cubed kind of starts as my main function, and then the derivative of x cubed is 3x squared dx. So this is kind of basically 1/3 of what you need there. So what you should get here is 1/3 e to the x cubed plus c. Then we're going to divide by e to the x cubed. So again, just to show that, well, I mean, you're dividing everything, so I'll write it out separately, but dividing by e to the x cubed. These cancel, this becomes a negative power. So what we end up with is y equals 1/3 plus c e to the negative x cubed. And that is our solution. Sweet. So again, as long as we can figure out it's linear in first order and it's in that nice, that nice setup, then figure out your integrating factor, multiply both sides, and so we don't need too many more of these. So that's part of what I'm saying there. Then is as long as you get it set up like that, then that's actually it. So the nice thing about linear first order differential equations is this integrating factor technique kind of does the whole thing for you. It is very much the same, pretty much every time. So, for instance, actually, which one do we want to do here? Mhm. Give me a second. Mhm. Mhm. Yeah, let's do something a lot more interesting. Well, they probably didn't mess with any of the other rules. All right, give me a second. And then what about? So we just need to do one or two of those. Come on. They give me some better options for things. Which one do I want to do? All right. So again, as long as we can set it up this beautiful way, then we can get it solved. So let's look at 17. Starts with cosine of x, dy dx. Sine plus sine of x times y, and all that equals 1. Now notice this looks a good bit different. So in some ways, again, with the previous lecture when we were talking about separable equations, it was like we had those first few very simple examples, nice form, and then it wasn't a nice form. We had to go and rearrange stuff and see if we could get it to be separable, right? So same, even in math, this is just strategy, same strategy here. So again, first two, very nice form, and to show you the form that we need. So here, we don't have that nice form. We have something in front of dy dx. And And then we'll kind of eventually talk about this thing in front of y. But especially the bigger issue is that we have something in front of dy dx, and we're not, or we can't have that to do our integrating factor. However, we can rearrange stuff, so that your next thought, again, your next step is just strategy of, could I get rid of this? If I get rid of this, then does everything else check out? Does it fit the form that I need? So could we get rid of this? If so, how would we get rid of this? Good, we could divide by cosine of x. So I could just divide everything by cosine of x. So, and I will make a point of kind of writing that out because we want to look at the results of this all the way down. We're going to divide everything by cosine of x. Now, it does achieve what I want. What do you call it? It achieves what I want on the first term here. I've got nothing in front of my derivative. Now, when we get to this, we have sine over cosine, sine of x over cosine of x. What is that actually? Good, that's actually a tangent. That's tangent of x times y. And then same deal, what about 1 over cosine? What is that? Good, that's actually secant. All right, now notice we now have derivative, nothing in front of the derivative, derivative plus something times y equals another thing over here. So this does seem to fit the form. It's first order, nothing in front of our first derivative there. And so now let's look at this tangent x that's in front of y. Again, to be linear, you're actually, what you're really looking at is the coefficient in front of here. Again, now it's not a number, it's a function. But as long as that function is a function of x, then we're good. It's linear. So this is indeed a linear first order differential equation with nothing in front of dy dx or in front of y prime. So we are gravy. We can form the integrating factor and go from there. Let's play that out. So my integrating factor is going to be, so this is now my phi of x. My integrating factor is e to the integral of nx dx. And yeah. And then now we got to kind of figure out this part. E to the integral of tan x. Or just face of the integral of tan. So we need something that when you take the derivative, get. And so this one is going to take a second for you to dig and remember. So actually, I want you guys to take a second. If you don't remember it right away, there should be an appendix in this book, actually, with integrals and derivatives. Or maybe Google one online, but pause on your side, pause on my side. Let's figure out the integral of tangents. All right, so the integral here, it ends up being, so this ends up being e, the natural log of the absolute value of secant x. And then I think there's actually a couple other formulations, but this is the one that gets used most often. It's helpful here too because we know that we're going to be doing some algebra kind of down here. Yeah, we're going to be doing some algebra down here with other trig functions. So we want to have a trig function there. So we can start to eliminate stuff. And notice that, again, e and natural log are going to cancel out. So again, without losing anything conceptually or theoretically, this just basically reduces to secant x. And if that is secant x, actually I do hold on a minute. because there is an alternative version that you could also, it could also be the natural log, negative natural log of cosine x. Well, no, it's the same thing. Okay, so yeah, it's the same thing either way. Okay. All right. Good stuff. So we basically end up with secant x out of this. So now what I'm going to do is I'm going to multiply secant x times everything. So see, we're going to have secant x dy dx plus secant x tan x y, all of this, and actually, so I'm kind of running out of room here. Then I'm going to multiply this, actually all going to equal secant squared x. So let me put a little delineation there that that's not part of the equation. Good. So that'll equal secant squared x. And then again, you're going to be tempted to think this is funky. Actually, wait, how much? Yeah, you're going to be tempted to think this is funky, but this actually works out. So again, the amazing thing is this integrating factor, as long as it's linear, first order, and standard form, every single time this is going to be a derivative of two functions multiplied. And you can kind of do the work from there. So I actually want to see if you guys can finish this out from there then. So again, the hint, not just the hint, the thing is that this left side is going to be the derivative of two functions multiplied. And then you can kind of work it out from there. So I'll pause, you pause, go ahead and see if you can work the rest of that problem out. All right, so let's see what you got. So on the left here, so the kicker is basically is just remembering or knowing that the derivative of secant is secant tangent. So this is actually exactly what we need it to be. So this is the derivative of secant. So this is a derivative times the function y. This is secant times the derivative of y. So this all together is d dx, the derivative of secant x times y. And then we can take the integral of that, as well as the secant squared x. And so the integral on the left side is going to be secant x times y. The integral on the right side is going to be tangent x, because the derivative of tangent is secant squared, plus c. And then we're going to divide both sides by secant. So divide by secant, divide by secant. And so if you work all the trig out there, I try to get back to a marker that'll work for us. First, see if the green works here. Actually, I think I need to move that camera for y'all. Then we know that y equals. So the fun thing is tangent over secant. Secant's 1 over cosine, so you flip that. Tangent is sine over cosine, so this just ends up being sine of x. And then c over secant. Again, secant is 1 over cosine, so you end up with c cosine x. And that is your answer. Let's see how well you can. Yeah, you guys can see that well enough. Sweet. Good. Yeah, so the big thing here is if you don't start in standard form, you can easily get it there. Essentially, you really just have to divide down by whatever's in front of that dy there, so the y. Okay, so with all that in mind, let's do one more problem. Do a initial value problem. So let's do something like that. 27 and 27 is set up. We have x, y prime plus y equals e to the x. And y of 1 equals 2. So that is our initial condition. So again, your goal here now is not to get a general solution, but with this, the general constant in there, but an exact solution. So you want to get the general solution first, and then use this information to plug everything, to plug things in and find C. So I actually want to leave this all to you. So pause on your side, I'll pause on my side. See if you can work this all the way through. Again, notice that the difference here is I do have something in front of y prime, so the first thing you want to do is divide that off and then work from there. So let's pause and let's see what you get. Let's see what you got. So, but first we need to divide everything by x. All right, so we end up with y prime plus, I'll write it out this way, 1 over x, y, and then kind of 1 over x, e to the x. It's fine enough. But this puts us in standard form. It's definitely first order, it's linear, 1 over x is good, that's a function of x. So this is my p of x. So my integrating factor is e to the integral of 1 over x dx. So a bit like the last one, that's e to the natural log of x. And that is just x. Oh, you know what I didn't see about this? Okay, my bad. I made this more complicated than it needed to be, but that's okay. Interesting. Okay. We'll have 1 equals 2. Let me make sure that initial condition is right. So of course I had to choose not wonky, but but this one is in some senses it's trying to tell a joke, basically. So notice that we kind of got back in some sense what we put in, or at least we divided by an x to begin with, but now we're gonna have to multiply back through by an x. So if you do that, we end up with actually the same thing. So x, y prime, and then the x is going to cancel out the 1 over x, so we'll just end up with y. Same on the right, so we'll end up with e to the x. So I see that as a problem solver, I see that, and I'm like, okay, either I did something wrong or I didn't catch something. And the thing is, though, this integrating factor, that's never going to be a wrong move. So we didn't do anything wrong, but we didn't catch something, or I didn't catch something. What I didn't catch is that what this means essentially is, again, ultimately I'm looking for this left side to be the derivative of two functions multiplied. So I'm looking for it to be one function times the derivative of the second, and then vice versa, plus second function times the derivative of the first. Look at so looking at this, what would our two functions be? So we know one of them is y, because we got a y prime. So that means the other function should be x, and what is the derivative of x? It's 1. So notice that we actually technically do have the derivative of x in front of 1. And I didn't see that video. I kind of was like, I just was running procedure, right? What that means is that I can rewrite this as d dx of x times y, and then go ahead and do my integral work. Oh, this is the way it is. Okay. What it leaves me with is xy on the left. And then the integral of e to the x is e to the x plus c. And then I'll divide by x. What I end up getting is y equals e to the x over x plus, and again, I'm going to write this as a negative exponent. And that is my general solution. That, however, is not the exact solution. So now what I need to do is I need to feed this information, y of 1 equals 2, into this. Make sure this still is, we see everything. Yeah. So I need to feed that in. So I'm going to plug in 1 for x, 2 for y, so 2 equals e to the 1 over 1 plus c times 1 over 1. So c, yeah, so basically times 1. You don't have to write I know we all know that that just becomes c, but I guess because I wrote it here, I just wanted it to be matched or be symmetric. So we end up with 2 equals e plus c. So c then is going to have to equal 2 minus e. I can plug that back into my general form and we get our exact solution. So our exact solution is y equals e to the x over x plus, actually, so now let's actually write it out this way. 2 minus e over x. So the x, the negative 1. If you want, you can actually combine these together. We could at this point. So yeah, let's do that. So y equals e to the x plus 2 minus e all over x. And that is our exact solution. All right. So again, like I said at the end of the last lecture, we'll probably do 1 or 2, well, so far 1, what do you call it, initial value problems every time, just because they're easy enough to do once you know how to do the general problem. You just tack on that work at the end. And again, because in reality, when you're playing these out, doing some physics, some chemistry, some engineering, when you're solving these, you're usually gonna have an initial condition, so you get an exact solution. So just to get you a little practice for that. All right, good stuff. But that is first order linear equations. And I will see you next time for exact equations. That is the next one. All right, see you guys then.